All right, today we're jumping into a huge question, one that literally powers our entire world. What is electric current?
You've done this, right? You connect a little bulb to a battery and boom, it lights up. But have you ever stopped to think about why? I mean, what is actually happening inside those wires? What's flowing through there to make it glow? Well, that's the big mystery we're going to solve today.
So where do we even start looking for clues? Believe it or not, we don't start with the circuit. We start by looking up at the sky. I mean, think about lightning. It's this incredible, powerful display of electric charge on the move. You've got a massive amount of charge just zapping from a cloud to the ground. So right away, that gives us our first big clue. Whatever this current thing is, it has something to do with charge being in motion.
Okay, so charge and motion. Easy enough, right? But wait a second. Does that mean anytime a charge moves, it's an electric current? Is a lightning strike the same as what's happening in that little wire connected to the bulb? This is where it gets interesting.
All right, to really figure this out, we're going to play detective. We've got a little experiment with 3 different setups. Think of it like we're investigating a crime scene, and the glowing bulb is our key witness. We need to find out exactly what conditions make it talk. Okay, situation 1. This is our perfect setup. We've got a battery, some copper wires, a switch, and our bulb. Everything's connected just right. We flick the switch, and yep, it glows, just like we expected. This is our baseline, our control group.
All right, test number 2. Let's try something. We're going to take out the battery. Everything else stays the same. Flip the switch, and nothing. The bulb is completely dark. So clue number 1, and it's a big one, you've got to have an energy source. That battery is doing something absolutely crucial.
Okay, for our last test, we'll put the battery back in so the energy source is there. But this time, we're going to swap out those copper wires for some nylon wires. Let's see what happens. Flip the switch, and still nothing. Whoa. Okay, so this is another huge clue. It's not just about having energy. The pathway the energy takes is just as important.
So let's look at what we've found. The bulb only works when we have 2 things, an energy source, our battery, and the right kind of path, like that copper wire. So what's the deal with copper? Why does it work when nylon doesn't? To figure that out, we have to go microscopic. Okay, so the big difference between copper and nylon all comes down to what's happening at the atomic level. And honestly, it's kind of like the difference between a massive, multi-lane highway and a quiet little dead-end street.
So materials like our copper wire are called conductors. They're the superhighways. Why? Because they are packed with these things called free electrons. These are little charged particles that aren't tied down to one atom. They're free to just roam around. Now, on the other side, you have materials like nylon. We call those non-conductors or insulators. In them, the electrons are totally locked down. They're stuck to their atoms and can't go anywhere. No highway here, just a dead end.
And this isn't some brand new idea, by the way. Way back around 1900, 2 scientists, Drude and Lorentz, came up with this model. They imagined a metal wire as this fixed structure of positive ions, kind of like buoys in the ocean, with a whole sea of free electrons just flowing all around them. And that sea of electrons, that's the magic ingredient.
Okay, so we've got our sea of free electrons in the copper wire. But hold on, we already said that just having motion isn't the whole story, right? So what's the final, missing piece of this puzzle? Well, it all boils down to one thing, the difference between total chaos and perfect order.
And this is where we have to clear up a really common misconception. You might think that in a regular piece of copper wire, all the electrons are just sitting still. Nope, they are actually whizzing around like crazy, bouncing off everything. But, and this is the key part, their movement is totally random. For every electron that zips to the left, there's another one zipping to the right, up, down, all over the place. So if you look at any one spot in the wire, the net flow of charge is 0. Nothing's really going anywhere. So even though there's tons of motion, there is no electric current.
So this is where our battery comes in. The moment you connect it, it creates something called an electric field inside that wire. You can think of it like an invisible force that suddenly gives all those chaotic, free-roaming electrons a command. It says, hey, everyone, line up and move this way. All of a sudden, that random buzzing turns into an orderly, one-way march. This ordered movement is often called drift. The battery literally turns chaos into order. And there we have it. We've collected all the clues. We know we need free electrons, we know we need an energy source, and now we know the real secret is about their motion. I think we're finally ready to put it all together. Think about the journey we just took. We started with a simple glowing bulb. That led us to realize we need a battery for energy. And we need a special path, a conductor, because it's full of free electrons. But the final, most important clue of all was discovering that those electrons can't just move randomly. They have to be organized into an orderly, one-way flow. So, here it is, the big definition you need to remember. What is electric current? It is simply the ordered motion of charges. That's it. It's not just any motion. It's not random motion. It has to be ordered. That one little word makes all the difference, and it's the entire reason our bulb lights up. All right, let's lock this in, especially for anyone studying for exams. Here are the key takeaways. Number 1, electric current is the ordered motion of charges. Got it? Ordered. Number 2, a battery is what provides the energy to create that ordered motion. Number 3, you need conductors for this to happen, because they're the ones with the all-important free electrons. And finally, remember this. In an open circuit or just a plain wire, the electron motion is random, which means the net current is 0. Simple as that. So now we know what current is. But that just opens up a whole new can of worms, doesn't it? Like, how can we actually measure this flow? What are the units? And what happens when those orderly electrons start bumping into things along the way? Well, that's a story for another time.